Assalamu alaikum. Welcome, dear students, to our second part in chapter 15, rectilinear motion. By the end of this video, you will be able to determine the characteristics and the time equation of uniform rectilinear motion URM. Let's start by reviewing together the main objectives of the previous video. In the previous video, we've studied the three types of rectilinear motion, which is the motion along a straight line. For a uniform rectilinear motion, the instantaneous speed is increasing with a constant rate. For a uniform rectilinear motion, the instantaneous speed is constant during the time. For a uniform decelerated rectilinear motion, the instantaneous speed is decreasing with a constant rate. Now let's start with our objective, which is to be able to plot the VT curve and the XT curve for a uniform rectilinear motion, then deduce from them the time equations of motion for a uniform rectilinear motion, V as a function of t and x as a function of t. In the previous video, we've recorded the driver's speed when he was moving in a uniform rectilinear motion at successive instants separated by equal intervals of time. All we need to do now is to draw the curve showing the variation of V as a function of time, in other words, the VT curve. After choosing a convenient scale, we start plotting the points, then we join the points to obtain a horizontal straight line parallel to the time axis. This equation had the form V equal constant. In our case, it is equal to 12 meters per second. Since the algebraic value of the velocity is positive, then, as we have learned in the previous video, the motion is in the positive direction, which means that the VT curve for a uniform rectilinear motion in the positive direction is a horizontal straight line situated above the time axis. What about if the object moves in the negative direction with a constant speed? Since the motion is in the negative direction, then as we have learned in the previous video, the algebraic value of the velocity is negative, and the VT curve will be then a horizontal straight line situated below the time axis. Now to plot the XT curve for a uniform rectilinear motion, we start by choosing a space frame of reference. We will choose the x-axis of origin O. Here we started timing when the object is on the origin, which means that the initial abscissa is x0 equal to 0. Let's fill the table with the abscissas at the different instants. It is given that each square corresponds to 6 meters. Then, at T1, x1 equal to 12 meters. At T2, x2 equal to 24 meters. And that's how we fill the table. After filling the table in order to deduce the xt time equation for a uniform rectilinear motion, we need to plot the points in this way. After that, we join the points and we obtain an increasing straight line passing through the origin. Then the equation had the form y equal ax, where y is the abscissa x and x is the time t. A is the slope of the curve, which is equal to delta x divided by delta t. You can choose any 2 points. In our case, we will choose the points at the instant t1 and t2. The obtained value is 12 meters per second, which is equal to the algebraic value of the velocity, which is equal to v. Also, you can deduce that the slope is v by noticing the units. Since delta x is in meter and delta t is in second, then the obtained unit of the slope is meter per second. Then the equation had the form of x of t is equal to vt. What if the origin of time is not chosen at the origin of space? In this case, we will start timing when the object is at 18 meters from the origin O. Then, the initial abscissa is x0 equal to 18 meters. We will fill the table by the abscissas at the different instants. At T1, x1 is equal to 12 plus 18, which is equal to 30 meters. Similarly, we calculate the other abscissas and we fill them in the table. After plotting the points and joining them, we notice that the xt curve in this case is an increasing straight line not passing through the origin. Then it is of equation y equal ax plus b. Similarly, y represents the abscissa x and x represents the time t. What about B? B is actually the y-intercept. From the graph, the y-intercept is 18, which is the abscissa at the initial instant t0. Then the y-intercept B is x0, the initial abscissa. And A is the slope of the curve. Then also, as we have worked in the previous slide, A represents the algebraic value of the velocity v. Then the obtained equation is of the form x equal vt plus x0. Note that the previous equation is a special case from this equation, which corresponds to the case where x0 is equal to 0. In the previous two cases, the object was moving in the positive direction, then v is positive, which means that the slope of the curve is positive, and that's why we obtained an increasing straight line of positive slope. What about the shape of the curve when the object moves in the negative direction? In this case, we notice that x decreases with time, which implies that v is negative. In this case, since the slope of the curve, which is equal to v, is negative, then the obtained curve will be a decreasing straight line, as you can see in this figure. And also the y-intercept is the initial position x0 at t equal to 0. Now let's start practicing by solving application 1. Don't forget to pause the video and try to solve the application by yourself. In the first application, you are asked to fill in the following table where all the cases correspond to a uniform rectilinear motion. You need to deduce from the curve the sign of x0, the sign of v, and whether the motion is in the positive or negative direction, also whether it is moving towards or away from the origin of abscissa. In the first curve, it's clearly that x0 has a positive value, and since the line is an increasing line, then it is of positive slope, and the slope in this case is v, then v is positive. Since v is positive, then the object is moving in the positive direction, and since the value of the abscissa increases, then the object moves away from the origin. In the second case, also x is positive, x0 is positive, and since the curve is a decreasing straight line, then its slope is negative, which means that v is negative. In this case, since v is negative, then the object is moving in the negative direction, and since the value of the abscissa decreases, then the object is moving towards the origin. It is decreasing from a positive value toward the 0, then it is moving toward the origin. In the third case, x0 is negative, but the line is an increasing straight line, then it is of positive slope, then v is positive, and the object is moving in the positive direction. But since the abscissa is increasing, since we know that in the negative direction, as we get closer to the origin, the value of the abscissa increases, then the object is getting toward the origin. In the same application, we have two objects A and B in motion. We need to indicate the sign of the initial abscissa of both curves A and B, the sign of the speed of both curves A and B, then compare their speeds and indicate the variation of the speed with respect to time. For curve A, x0a is equal to 0 since the curve is passing through the origin, and since it is an increasing straight line, then its slope is positive, which means that VA is positive. Also, for curve B, x0b is equal to 0 since it is passing through the origin, and since the curve is an increasing straight line, then VB is positive. But here notice that curve A is steeper than curve B. In other words, A is much closer to the y-axis than B. In this case, we know in mathematics that the slope of curve A is greater than the slope of curve B, which means that VA is greater than VB. This indicates that between two xt curves in a uniform rectilinear motion, the steeper graph, which is closer to the y-axis, is of greater slope, which means the greater speed. Now, in both cases, v remains constant with time, since it is a uniform rectilinear motion. Now, let's move to application 2. Consider an object M moving along the x-axis. The time equation of the motion of M is x equal 5t minus 15 SI units, which means that all the factors are in the SI unit. In the first part, you are asked to specify the nature and the type of motion of M. Since the time equation had the form of x equal vt plus x0, then the motion of m is a uniform rectilinear motion. In part 2.1, you are asked to indicate the algebraic value of the velocity and the initial abscissa of m. To indicate the values, we compare the two equations x equal 5t minus 15 with the equation x equal vt plus x0. By comparison, v equal 5 meter per second and x0 equal minus 15 meter. In the last part, you are asked to deduce whether m is moving in the positive or negative direction. From the equation, v, which is equal to 5 meter per second, is positive, then m moves in the positive direction. Let's have another application. In this application, a car traveling on a straight road at a constant speed passes a traffic light. Take as a frame of reference the horizontal axis OI directed positively in the direction of motion, where O is the position of the traffic light. The adjacent graph represents the variation of the position of the car with respect to time. In the first part, you are asked to refer to the graph to determine the distance between the car and the traffic light at t equal to 0 second. From the graph, at t equal to 0 second, x0 is equal to 2 multiplied by 100, as you can see on the y-axis, which is equal to 200 meter. In part 2, you are asked to determine the speed of the car. The speed of the car is the slope of this line or this curve. Then v car is equal to delta x divided by delta t. You can choose any point from the graph. I will choose the point 510. And after calculating delta x, 500 minus 200 meter divided by 10 minus 0, I will obtain 30 meter per second. Now we are asked to write the time equation x as a function of t for this curve. In a uniform rectilinear motion, the equation is of the form x equal vt plus x0. V is calculated and measured to be 30 meter per second and x0 is 200. Then the equation is x equal 30t plus 200 SI unit. In part 3.1, we need to determine the position of the car after 2 minutes. They gave us the instant. We need to calculate the position on it. Don't forget that the position is x. Then x at t equal 2 minutes, which means 120 seconds, is equal to vt plus x0, which is equal to 30 multiplied by 120 plus 200, which gives us 3,800 meter. Now we need to deduce the distance traveled by the car during the 2 minutes. The distance d is equal to x minus x0, which is equal to 3,800 meter minus 200 meter, which means that the car covers 3,600 meter in these 2 minutes. Now you need to determine the acceleration of the car. A is calculated by dividing delta v by delta t, but since v is constant, then delta v is equal to 0, which gives us that A equals 0 meter per second square. Now let's summarize the ideas of this video. In a uniform rectilinear motion, the trajectory is a straight line. The speed remains constant with time, which means that v average is equal to v instantaneous. The vt curve is a horizontal line parallel to the x-axis. The xt curve is a linear function, which means that x varies linearly with time. The time equations of motion are x is equal to vt plus x0, v equal to constant, and a equal to 0. In a uniform rectilinear motion in the positive direction, the algebraic value of the speed is constant and positive. Then it is a horizontal straight line situated above the time axis. And the xt curve of equation x equal vt plus x0 is an increasing straight line with positive slope. In a uniform rectilinear motion in the negative direction, the vt curve is a horizontal straight line situated below the time axis, where also v is constant, and the xt curve is a decreasing straight line of negative slope. Since v is equal to constant, then A equal delta V divided by delta T is equal to 0 meter per second square, which means that in a uniform rectilinear motion, the acceleration A is null. This is the end of part 2. Thanks for your attention.